essentially, it takes the prototype of an idea that would have been presented by the pre-form that the economics would have presented, and it creates a bridge between that prototype and satisfying that product, some kind of scale, right, on industry. And in doing so, it uses design for manufacturing, basically in a sustainable way, or at least that's what the industry is, aiming to do now, to bridge that gap between that prototype and that idea at an industrial level. Of course, if someone intends on expanding, converting, or even reducing their manufacturing system, they may be hit with certain challenges. These challenges usually sometimes umbrella under things like excessive resources or the amount of resources that they may need to enact these kinds of changes. It may take time, right? If you're in a plant, or if, for example, where I worked in Ministry of Roads and Transport, we needed to analyze the maintenance system of our vehicles, right? So we needed time to convert, all right, if we're reducing it to scale, if we're adding class 3, class 1 vehicles from one point to another, to pretty much optimize the system based on the resources that we had. And of course, it takes money, right? It takes money to do these conversions. It takes money to hire technicians, hire analysts, and do all these things to measure, perform, optimize the systems to ensure that they work with the system that we actually want to work. So that is a quick refresh on what a manufacturing system is. Right? Once again, question of machines, processes, resources to realize or create some kind of product or service. Now, this is where the virtualization or virtualizing manufacturing comes in. Because similar to how we have seen where we took an actual preform or an actual product and created it in a CAD software, similar to how some persons may look at a shoreline and virtualize it using simulation to get a number of different ideas, a number of different measurements going forward. Similar to how, let me move this right here, similar to how you may see a room or office space, and using virtual reality, you may virtualize that to get a more intrinsic idea for further editing in case you want to make any renovations. This is what we use to virtualize, or this is the approach that we're intending to use, right? To virtualize an actual production or manufacturing system into a simulation for these intents and purposes, from actual to virtual, using some kind of computer integrated approach, integrated manufacturing. So once again, we're taking this prototype of an idea, but instead of just using design for manufacturing using a sustainable way, we're using this kind of design for manufacturing, but using simulation. And as a result, the challenges, and of course there are many more challenges, but generally these challenges, resource hungry, time consuming, and cost that we're looking at, it is no longer challenging or as challenging. It may not be as impossible, because by using simulation, you're going to see very shortly a demonstration of this application. We're essentially making it relatively easier, right? Albeit there may be some kind of thoughts and different prerequisites that we may need to enact this, right? But we're essentially making it less impossible. Just like, for example, a case study. Let's say we have a manufacturing facility, right? For avoidance of copyright purposes, we're going to call this Coca-Cola, right? And we're actually looking specifically at their injection or plastic injection molding facility. Now, this facility, this subset is used to create a certain aspect of it. In this case, for example, a preform that may be used to, in the end, manufacture the end product, which is the bottle. Now, they may be integrating certain technologies for their manufacturing system. They may be using or trying to effectively use adequate resources to save on time, cost, and at the same time, they may be applying as much as possible industry standards, right, to abide by certain principles. So, in that case, they're applying all of these policies, or at least trying to, make them work. But let's say they wanted to measure and optimize the performance of this plastic injection molding process in the injection molding department. They may have the machines, they may have the raw material going from the input straight to the process, going to the output, maybe optimizing, or rather more specifically, measuring the performance of cycle time, maybe looking at the waiting time, all of the non-value added and added value, value added activity. For those who do not understand what that is, value added activity is everything that positively contributes to the manufacturing process, right? Non-value added activity or waiting time is the delays that may occur. So let's say they want to measure and optimize this performance. Well, how would they do that? So in this regard, this is where we apply simulation. Right. So as the material comes in, it actually interacts with every single process that you may see, right, inside the actual manufacturing system. Now, it may come, if we have two separate lines, the red dots may come from line A, which is right here. Then it may come, other lines or other material may come from line B. Now, what this is showing, for example, and you can clearly see this, is that there seems to be some kind of bottleneck at one of the cells. Now, what could this mean? This could mean that in the existing manufacturing system, it may be waiting on a particular batch or a set of different entities or raw material to come in before going to the next stage. It may mean that a technician may be taking a little too long than usual before going or carrying the products from point A to point B. And eventually, what this kind of manufacturing or simulation can do, or how it can be used, that it can measure all the things that I would have mentioned, such as the waiting time, the value added activity, the cycle time, the queue time. If, for example, each particular cell is working with a technician, a machine, or collection of these things. And by doing so, you will be able to understand, okay, these are where the bottlenecks are really taking place, as opposed to where a practitioner, a technician, an engineer may think the bottleneck is actually taking place. Because one of the differences with regards to manufacturing or actual system is that you may see visually that, okay, it may have been occurring at this point, at this pink cell here, right? That's what they may have been assuming, right? But in the end, the real actual kickback or the setback, as we're seeing here, is occurring at the inspection line. So what does this mean? Well, essentially, what this may mean is that the technician, once again, may be taking a little longer than usual to inspect all the preforms that are coming in into this section of the manufacturing process. Or it could mean that they may hit a snag. And as a result, what can be done? Possibly add a different technician, add a particular automated system to improve the inspection line, or many other things. For example, change the line, change the design of the manufacturing layout. This is an example of how we can apply the simulation to really optimize, or rather measure, analyze, and optimize the production system. So that in the end, we may save on certain things as opposed to implementing and physically changing the layout to then optimize, measure, and see the end result, right? So for example, after all that time, it took the red raw material from the line A to go to this, the process, and then the other set of materials coming from line B. So as a result of this kind of application or this kind of overview, right, we can actually just measure, see things like, once again, the waiting time, non-value added activity, add, change the manufacturing flow, the resources that are being used, be it they are scheduled or not. And we can actually scale this up. Remember, once again, we're using design for manufacturing in a sustainable way, using simulation to satisfy the items of industrial scale. So we're taking the prototype of an idea, and we can scale this up to millions upon millions or even hundreds of thousands of entities to simulate it. And once again, one of the unfortunate setbacks with regards to what many of the industries, for those who are students, when you graduate, you may face this in the world. For those who are already working, one of the setbacks is that for small and medium enterprises, they may think that they may not need this kind of simulation. This may be more suited for much larger industrial complexes. However, that is not the case. By using simulation, you can save on money in terms of profit. You can maximize that profit by reducing waste as much as possible, because in the end, it's all about maximizing profit for maximum efficiency. So I hope that you actually enjoyed or got some kind of insight into how we can use this type of simulation. Right? Once again, it's not about the type of software that's being used, right? But it's about the approach and using simulation to solve these kinds of industrial challenges, be it for expansion, reduction, or modification. So going back to the presentation, right? In conclusion, some of the requirements that someone may need to actually get involved and apply these kinds of applications or practices for their existing system, if they want to create something of their own, is rather understanding the fundamentals in designing and developing a product. You have to, of course, know how your product is made. Once again, taking the idea from the prototype to the industrial scale, right? At any different kind of degree or level, it is important to have the knowledge of saving resources, right? Because if you have an idea of, okay, if you run your simulation and you don't know how to save on those resources or apply lean thinking or resource saving strategies, then what are you really getting from that kind of simulation, right? What kind of performance or measures you're expecting to absorb from that simulation? Thirdly, you have to know the applications of manufacturing technology, right? What kind of machines maybe, or you may be thinking of using. If you were to implement or some kind of strategy, you run your simulation, all right, you may identify these kinds of bottlenecks. The machines may be old, may be having some kind of delayed time. Well, you have to know what kind of technology to be used to replace that kind of machine or that kind of resource to maximize or improve on your performance. So obviously, of course, the benefits that should come out of this would be an optimal use of the resources. You're saving on time in terms of modifications of your existing system by running the simulations, because that will arguably be done a lot faster when you are intending on growing, expanding, or reducing your actual system. And of course, you will have, or you should save on money, right? That part is always tricky, and it's always very, very dependent on the simulation that you're actually using, and of course the actual manufacturing system. Because, for example, you're not gonna spend thousands of dollars or even hundreds of dollars on a simulation software to optimize a very small change in your system, right? So I hope that this has offered some insight into the applications of using simulation to solve systems or solve challenges like these. And I open the floor up to anybody that may have any questions whatsoever. Yeah.
Does that have to be for production facility or like hospitals?
That's a good question.
Because the products have to be something that like a patient.
Right, that's a very good question. So that's quite true. Given that this type of software is, given that it's looking and measuring certain things